Hello everyone, my name is Abdel-Rahman, and today I'm going to help beginners how to start using EGSnrc to do some simulations. In the previous videos I focused on installing EGS on your computers, and I've also demonstrated how one can create PEGS data files, but now I want to go to the next step, is to run just help you start your first simulation. There are several user codes that come with EGS that are commonly used by users, but for advanced users they can actually write or create their own user code. A user code is basically the executable that one is going to run. That executable will contain the physics that needed to transport the particles. It will also contain the general geometrical module for transporting the particles in. So another thing in the executable will be what are the input variables that the user needs to supply, and what are the output results that the simulation is going to calculate at the end of running the simulation. You can always refer to the manual to understand how the EGS system works. With EGS comes several user codes that are commonly used by a lot of researchers. Today I'm going to demonstrate in my opinion, this is the simplest one. It's dosrznrc user code. So to do that, you will probably have icons on your desktop. So we will need to open the EGS underscore input RZ. So once you open that, it will probably open the default input, the default user code. These are the user codes that run using an RZ geometry that are pre-built and compiled with once you install the EGS package. So those RZ is the most common one, but SPRRZ NRC is another common one. This is used to calculate stopping power ratios. If you hover over the user code, there is some information there. So CAV-RZ calculates quantities of interest for high cylindrical ion chambers, and FLU-RZ is fluence spectra scored by summing track length in a zone. But the one we're going to run now is the dosrz dosrz NRC. So this is highlighted or selected. Target, just use no optimization, or leave everything as default. Optimization, user code area, leave as default. X home, and the PEGS data area is also leave it as default. Hen house. You will also find here, this is the template, a template for an input file, and this is the default PEGS4 data file that has the PEGS data for the materials that we're going to run here. So you leave everything as default. Make sure that the execute button is clickable. If not, probably you will need to compile. So that's simple. You probably just hit compile and wait for the compilation to finish. Exit the user interface and launch it again. You will then find the execute button clickable or enabled. So this is the first tab that has the general information. I'm going to leave this, or if you want, we can leave the default template and maybe just change the name. So we can put this my first file. Okay, it's an input file, and hit on save, click save. Okay, so now we go to the next tab. We'll leave everything as is. Monte Carlo. This here is the number of histories. I think the default in the default template you'll have 100 particles. This now is 100,000. So I'm going to put it back to 100. Okay, once you make a change, try to always save. Okay, and I'm not going to go through everything at this stage. I just want uh, to guide you just to launch your first simulation, and let's see what is coming from or what you should be getting from running the dosrznrc template. Now the geometry, that again I'm not going to go through it today, but this is where we're going to define the RZ, the radii and thicknesses of slabs, and assign the materials to that geometry. If you want to see how this looks like, then you can just click on the preview RZ button, and this is the RZ. So these are the slabs, and those are the either the cylinders or rings that we're going to score those in. Cavity and media definition, I think these are enabled if we're running cav RZ. So for those RZ, these are not enabled. Source, this is the source of particles. I think in the template it's a monoenergetic photon beam. So here is the particle type, photon, and monoenergetic. This is a mimics, or it's a cobalt source. And then the source type, there are several different source types. So 0 is basically we have a parallel beam incident from the front of our medium, and this is the radius of the beam is 5 centimeter, and this is the direction of the beam. So 1, I think these are cosines of the angles. So 1 means it's shooting down towards the beam. We will look into these in more details. Then we go to the transport parameters. This is where we control the physics. The most important thing, if you want to use the latest physics available with EGSnrc, is we need to make sure that boundary crossing is exact, and electron step algorithm, this is Presta 2. And another option is the spin effect. This this has to be on. Now, why do they have these options for users? Well, think about it. This code has been gone through a lot of development, and suppose today I want to actually recalculate something published, let's say 20 or 30 years ago, with an older version, just so that I can compare, for whatever interest that. So then I can actually change the physics and go back and use older algorithms that were used in those calculations, and to get the results and so on. So here's Brahmish. I'm going to leave everything by default, but please make sure they have exact here and Presta 2, and as well as the spin X on. If you want to include Rayleigh, if you photoelectric angular sampling, bound Compton, I personally like to keep it as on. So to use bound Compton, physics for bound Compton, You turn this on. This has effects usually at low energy X-rays, but not for uh, mega voltage like for cobalt and so on. It does not really have an effect there. Okay, so let's go to the variance reduction. Again, I'm not going to explain anything about these, about those techniques for the time being, but just leave whatever there is a default on. Plot control. This is, we want to we want to get PDDs. So a nice thing about those RZ is it can also produce the results in a format that is easily could be plotted with XM Grace. So here, for example, we're asking it to calculate. So these are to control radial. For example, we want to calculate plot the PDD along the first radial zone or the second. So let's preview RZ just so that we explain more what's about this. I'll try to zoom. So let's zoom this. Okay. So basically we have a region here. This is the center one is basically a cylinder. The cylinder has some radius, 1 centimeter radius. So this is a think about it, cylinder with a 2 centimeter diameter in the center. Then the next region, it's a ring. The ring has a dimension of 2 centimeters, of 1 centimeter. This is the inner R of the ring, and that's the outer R of the ring. So if we want to calculate PDDs, essentially we want to calculate or get the doses along in these zones, the first zone here. Okay, that represents a PDD. Now let's go back. So radial, this is the depth versus radial region. So if we go back, if this is 2, that means it's going to calculate the dose along these rings, and that's not really a PDD. It's not even, you cannot claim it's a profile of the beam. But maybe for interest, maybe if you have a device that scores a dose in a ring shaped region, then you might be interested to record those there. So the simulation will actually record the dose in all of these regions, but now I'm having the option, what do I want to be plotted? So for example here, probably I don't want this. I'm going to put this as 0, and the planar zone 10. What this means that, okay, along the 10th planar zone, it's going to calculate the dose as a function of R. Again, that is not a profile of the beam, but maybe for some other reasons one wants to plot this. So again, that is I think along the Z, along the 10th region. Okay, the planar IZ 10, this means plot the dose as a function of R for along the depth, along the depth zone of 10. So this means that if we look at the preview again, let's zoom. Okay. So this is, I believe, this is the 10th zone with respect to depth. So with that 10, this means that plot the dose in these regions. Okay, remember, this one is a disk. You can think of it as a disk, whereas these regions are rings that are surrounding this disk, this inner disk. Okay, so we're going to save, yes, and now we're going to execute the code. I just want to make one thing, input output. Okay, so we're going to execute, and we'll leave this as interactive and run. So now it has launched the simulation. It just puts out like a log file what's happening, and even in that file you'll find the physics information about many things about the geometry, about the physics that's being used, and then if there are warnings or errors, it will also provide that. And if everything is okay, you should start to see here the calculation, the batches. Usually the calculation is done under 10 batches, and of course the simulation was very quick because we have used 100 particles, and gives you at the end some information about the time elapsed to do the simulation and so on. Okay, so so that's the output. Now let's go and open dosrznrc, and now let's see the log file. So log more. Remember, we call this my first file, and if I put a dot, you'll see the files that are there. This is the input file that we have just created. If there are errors, it will be here. The list file is I think it's the log. Let's check. Okay, yes, this is basically a list of what's there. This is actually the output of the simulation, and here you can find the dose in all the regions that we have defined, and the mass of these regions. Okay, but there is a more useful so let's more the dat file, the xdat file, is basically the numbers that this is not a readable file to a user, but it's readable definitely to the user code. So if I want to restart the simulation to accumulate more histories to reduce the statistical uncertainty, then when the simulation launches, it's going to actually read the data from this file and then continue running the simulation. Okay, so there are two files. So this is the name, and then if I do an underscore, there you should find the dd, that's the depth dose file, and another one is the radial. So the first one is the the PDD for the central region, and the second one is it's not a profile, but it's a dose as a function of the radius at zone 10. So let's look at the file. This is the file. It's just a text file, and here you have for example, this is the center of the cavity, or depth. You can think of it as depth. This is the dose value, and this the statistical uncertainty. So this format is actually readable by EGSnrc. So if I type EGSnrc and we do this, then we get this plot. Of course, this is basically something that we don't recognize because we only ran 100 particles. But let's continue. Let's accumulate. Let's run 1,000,000 particles. So let's open again the file, and once you open it again, the default is still dosrz and dosrz template, but we want to actually go and open our file. So our file is my first file, okay, my first file, and then the input output control, I'm going to change this to restart. So this is to accumulate more particles, and then we'll go to Monte Carlo, and let me put 900. So now the total number of simulations, of histories simulated, is going to be 1000. So let's execute this, okay, and again look at, I hope there are no errors. Yeah, no errors. So let's look at the file again and see if we start to recognize what's okay. So now you see the difference. So instead of having just 2 doses there, now I'm getting something that, okay. So let's increase the number of histories. So let's put, so 9,000. The total is going to be 10,000. Simulation finished, and we open again. Okay, now we're starting to see something that resembles a percentage depth dose. Okay, so I will leave this to you. You can run this simulation to let's say 1,000,000 or 10,000,000 particles. One thing probably, those with parallel processing, if you want to do parallel processing, let me show you how to do that. So let's put 1,000,000, okay, and I'm going to save, but I also want to change this to first now. Okay, so with parallel processing, you start your initials. You cannot, for example, run a simulation single core and then resume the simulation by saying, okay, now I want to use multi-cores on that. It doesn't work this way. So you have to define the splitting number from the beginning, and you can accumulate using that same number of splits. So let's save. Okay, and I want you to watch here what's going to happen. Maybe I should, let's execute it, and I'll put it as interactive and hit run. So you see only the calculation is using one single core. So at 100%, I have 8 cores on this machine. So one single core, and the simulation is running. Okay, that's 9, and then we have the last batch to be calculated. Okay, now the calculation finished. So that's it. Now I can run it now in batch, okay, to use parallel processing, and this is the split number. So batch is basically to submit something in the background to be calculated. If you're using Linux, you want to submit the calculation and log out, then you can do that. You submit it with this batch option. But now we can also submit it with batch with parallel processing. So I have 8 cores. Makes sense. What makes sense is to use my full 8 cores to run the simulation. So I'm going to put this as 8, and let's hit on run, and look at this. So now the simulation is now running, submitted 1,000,000 histories, but now it's submitted on 8 cores, and you see immediately the calculation has finished. because each core has done 1/8 of the histories, approximately 1/8 of the histories. And I think it does combine the results at the end of the run. So if I do go and run exam grades, you see I have now really a good PDD curve with the error bars are smaller. So the uncertainties are smaller. Just note here, this is, I think, in this box, this is, I think, air in the default. So that's why you have this non-smooth jump, because I think that region is air. If you look at the preview RZ, and we put this at 40, 40, and apply. So this region is actually air. So here is the color code. This is water, and this one is air. Maybe in another video, then I will try to explain how you can define your own geometry and then assign different materials to these geometries. But for the time being, I hope this demonstration will help you to launch your first simulation and also to get at least the results. You can experiment. For example, what I would suggest is you can go to the source and probably you can make another file and maybe look at an electron beam, okay, and put the energy to be 10 MeV and launch the simulation, okay. But we will in future videos I will explain more about how to define the geometry and probably also look at different sources. For the time being, I would like to thank you for watching this demonstration. Please subscribe to the channel, hit the like button if you think this is useful, so that I can continue. I understand or know that you will need to see more videos like this, and you can hit on the notification button too. Thank you very much, and until next time.